All right, we're going to go ahead and finish up chapter 11, and we're going to talk about a different type of, well, it's not technically a solution, so it gets its own name. And let's go ahead and look at what this mixture is called. And these are called colloids, all right? And you've seen a lot of these, and we'll get into a few examples. But these are going to be mixtures that appear homogeneous. And when I talk about homogeneous or homogeneous, depending on how you want to pronounce it, that's where if you look at it, at one corner of the, let's say, glass or beaker, it looks exactly the same at another point. All right, so heterogeneous would mean something like, you know, a slurry or a suspension where things look different at different places. But here, the major difference is that the particles in the mixture are macroscopic. So that means they can either be seen with the naked eye or with a microscope. All right. If you were to take a homogeneous solution, like let's say we take sodium chloride and dissolve it in water, there's no microscope that could actually see the sodium ions floating around in the solution. So those would be considered nanoscopic. All right. Here we're looking at macroscopic, where we can actually see them with either the naked eye or the microscope. All right, and these particles are about quite a bit larger than a nanometer. All right, so we're not going to get into the actual specifics of the size of the particles and so forth, but I just want to talk about what kind of particles are in these mixtures. So the best way to talk about that is splitting them into what we call a dispersed phase and this is going to be akin to the solute. Now technically it's not a solute, all right, but it's what you would think of as a solute. It'll be the minor component of the mixture. And then you have something called the continuous phase. And again, these are mixtures that are not what we consider solutions, but if you were going to try to draw that parallel, the continuous phase would be similar to the solvent. All right, so a little bit different terminology here. So we have a dispersed phase and a continuous phase. All right, and depending on what kind of particles are in each phase, we get a different type of name of a colloid. So why don't we go ahead and make a table here and talk about a dispersed phase and the continuous phase. The name of this mixture, and let's talk about an example you may have seen. So here's our table. If we were to take liquid particles and disperse them in a continuum of gas, we call those aerosols. An example of that you've certainly seen is fog. All right, fog is a colloid. All right, they have liquid particles like water in a continuous phase gas, like the atmosphere, for example, and that would make us have fog. All right, we can reverse it where we have gas dispersed in a liquid continuum, and this is called a foam. And shaving cream or Ready Whip, things like that. So we'll say shaving cream would be an example of that colloid. All right. Another way we can look at colloids would be a solid dispersed within a liquid. And this is called a sol, S-O-L. All right. And soapy water would be an example of that. And finally, one of the more fun ones is when you have a solid dispersed in a liquid as well, but if the particle sizes are just right, you get something called a gel, all right? And Jello is an example of that, all right? So that's just to give you an idea of what some of these, colloids are like, all right? And what's really neat about colloids is they all exhibit this property called the Tyndall effect. And this is certainly something you may have seen in fog. All right. So what happens here is those particles in the dispersed phase are large enough to reflect light. So what we can see is a beam of light is visible in a colloid. All right. So, for example, if you were to take Jello here and have a light beam, all right, shining through, you would not see that light beam outside of the container, but inside the Jello, you would see that light beam actually being reflected in that Jello. So that's something you can try at home. You can certainly do that with fog. Shaving cream, it's a little more difficult because it's going to reflect so much light, you probably won't be able to see through it either. And then, what are some other ones? Soapy water, that's an easy one to make at home and try, as well as dust. A dusty room, okay? What you have there are solid particles dispersed in a gas continuum. So in the afternoon, sometimes you can actually see the sunbeams in a dusty room. All right, pretty neat, but probably need a clean house if you see those. All right. So another thing we're going to talk about with colloids are something called the particles that can disperse in them can be called micelles. If they are dispersed particles that aggregate via intermolecular forces. All right. So some of the particles will have attractive forces that are strong enough to actually tie them together. And one that certainly does that are going to be soap molecules. Now, the way soap works is if you look at the back of a typical soap bottle, you see something like sodium lauryl sulfate. All right. And those type of molecules, if you look at their line angle formula, have this, what we call hydrocarbon tail over here. And then the sodium ion would be coordinated here, all right, to that negative charge. And over here we have a polar head. All right, so on the left of my cartoon, I've got the hydrocarbon tail, and then on the right, I have the polar head. All right, so we can make a cartoon of this molecule, something like that. All right, so right here, we'd expect this to be nonpolar. That's the hydrocarbon tail. And this would be polar. And that's the what we call the polar head. All right, so that's where the charged end of the molecule is, so it's highly polarized there. Okay, so if we put this molecule into water, or several of these molecules, right, which part of the molecule is going to like water and which part of the molecule is not? All right, and the answer is the polar end is going to like it and the nonpolar end is going to avoid it. So how does this work? Well, what's going to happen is that the surface area of the polar heads are going to maximize their interaction with the water. Let me move this picture, sorry. So what we're going to have on the outside is water surrounding all these molecules. So I'm going to put H2O around here. And it's going to be the polar heads that are going to want to be near those, all right? But the hydrophobic or hydrocarbon tails are going to want to minimize their interaction. with the water, so they'll run away or turn inside and kind of hide away from the water. And what you get is this micelle. So it's a collection of the soap molecules that have aggregated into this very large particle that is now colloidal, all right? So this is how soapy water would reflect light. This colloidal micelle is large enough to reflect light coming through this water solution, and that's how the Tyndall effect works, all right? There are other types of micellular aggregates out there, you know, a lot in biochemistry, but we're just going to kind of just talk about one that works quite well, and that's the soap molecule, or sometimes you would call these surfactants. All right, those are synonymous terms in chemistry, so surfactant is a little more of a technical term for a soap, all right? So how does soap work? How does it clean things, right? So what it has the ability to do is it has the ability to pick up grease using water as your solvent, all right? So let's say you have a little oil stain or grease stain on your clothes, or on your hands, if you will, all right? So if you were to try to wash this off your hands with just water, of course the water would just run off of the oil, and it would take a very long time and an enormous amount of scrubbing to get this oil off your hand. It would never work to get it out of the fabric of your clothes. All right, so what happens if you actually take one of these micelles here of soap? Well, what they can do is they can break apart and then reform around the oil. So I'm going to color the oil in red here. So what I've got on this cartoon now is that the soap micelle has opened up and then reformed around the oil. Now the reason it forms like this is because that hydrocarbon tail right there on all these guys, remember they're non-polar, they're greasy, they like being around oil. So they'll break apart and then aggregate around that oil, and then you have all your water that is attracted to the polar head of the molecule, or micelle in this case. And now you have this even larger micelle that contains the oil stain, right? And it will wash away in the water, thus cleaning either your hands, your clothes, or other areas where you need to remove oil using water. All right, so pretty neat little way chemistry works here with colloids and thinking about intermolecular forces. All right, so that ends our discussion of chapter 11. The next video will start into chapter, we've been in chapter 12, pardon me. This last video was of chapter 12. We'll be moving into chapter 13 next, chemical kinetics. So it's going to be quite a bit different shift in the course. And this will also officially end our material for exam 1 that will be made available on Thursday. All right, so we'll start kinetics in the next chapter, but the kinetics will not appear on exam 1. All right, well, thank you very much.